Believe it or not, this is a public clock. It doesn't look like any clock I've seen before. In fact, it works by water power and gravity. It can't be just to tell you the time. Most of us can get that from our £5 digital watches, accurate to a few seconds a year. No, the designer of this clock must have had something more in mind than just the right time. The working mechanism is really quite simple, but it still amazes me that it works at all. The clock face at the top here tells you the hour, and below me you can read the minutes from the water tube lower down. During the course of each hour, the minute tube gradually fills with water. Getting the rate of refill here is important if the clock's going to be accurate. When the tube's full, a float at the top releases the water, which sets off a whole chain of events. Take the minute tube, for example. The designer had to get the rate of refill right. And there's a problem with algae growing in the system. How did he get the water volume right in the little buckets? What about evaporation in summer or freezing in winter? All pretty challenging stuff for the designer. In fact, the guy who designed this water clock designs and builds all sorts of weird and wonderful gadgets. And what we're going to do is find out how he tackles his own design project. It takes a whole series of different skills to make something like this: welding, carpentry, fabrication, and a well-developed sense of the absurd. In fact, it was designed and built by a man called Tim Hunkin, who, with a friend, Andy Plant, finished it in just 6 weeks.
I've always liked clocks, and I'd never made one before, but I think I'd always wanted to try one. I did it with a friend. I prefer working on big things with somebody else. It's just physically moving the stuff about is a lot easier with somebody else. I think we started off with the idea that it was going to cover the front of the building, something fairly large. And I'm sure at that stage the owner of the shop wasn't expecting anything so big, and we were amazed and delighted that he accepted it. And then I came back and spent 6 weeks or so sorting out lots of problems. Things like the figures were going to be three-dimensional, and the whole thing was in danger of covering most of the pavement. And we made them flat, and the tanks got thinner, and lots of the small things we worked out at that stage. We then put the thing up on the side of my barn as a prototype, and it didn't all work at first. The watering cans didn't work because airlocks got into the system. But we solved that by putting a little tube which drained the water out of all the pipes at the end of each cycle. It was at that stage that we really sorted out the total amount of water that would be trundling around the system and getting some idea of how long the cycle would take. The barn isn't as high as Mike's shop, so we couldn't have the bells above the dial, and in many detailed respects it wasn't the same, and that was why we had problems when we actually came to put it up. I remember we spent a long time trying to prevent any splashing occurring, putting baffles in, things like that. But in the event it does splash quite a bit, but people don't seem to mind. Then after we put it up, we still hadn't decided what to do in winter, but in the end we put an immersion heater in the tank, and it's never frozen, so that seems to have been solved. The flowers were quite a problem. Each had an individual float and a weight underneath, and it looked very nice, that, because they bobbed around as the watering cans bumped into them and things. But they tend to catch with each other, and they didn't come up very well. So we've now mounted them all on a single float, which does work a lot better. The whole thing at first got clagged up with sort of green slime, so we had to put some chlorine in the water to stop that happening. And that's attacked the paintwork. Don't know that there's any solution to that, because it's essential to stop the slime forming. So you just try and put in as little as possible. The main problem has been the minute tube, getting it to fill up with the right amount of water every hour consistently. However many filters we put in, it's very difficult to prevent something just getting in the critical hole and altering the rate. And there's still got a lot of niggling problems left. But it's very satisfying seeing the way people gather on the hour to watch it.
Niggling problems or not, there's always a crowd to watch the clock chime every hour on the hour. And people are fascinated by the ingenuity of the design.
People often ask me where I get my ideas from. It's not really as magical as it seems. The ideas don't generally come out of the blue. It's more a case of one thing leading to another. I do read quite a lot, keep myself up to date with catalogues and things, and I love looking at machines.
Museums are very good for ideas for my sort of clock, not only for practical ideas, ways of doing things, but also for silly ideas as well. This one's a 17th century turret clock from a church in Worcestershire. It may not have been very accurate, but it's obviously worked for a very long time. Accurate timekeeping's only been essential in the last 100 years, since the spread of railways, which meant we all had to keep the same time, and artificial lighting ended our dependence on daylight for working. Before that, clocks were generally toys of the rich, or objects of civic pride. In both cases, pomp and spectacle were at least as important as their ability to keep time accurately. This is what's called a congreve clock. The ball takes exactly 15 seconds to go from one end of the tray to the other. I like it being a bit of a puzzle to read the time on clocks. It makes you look at them a bit more closely. These Japanese clocks have a vertical scale, very useful because they used to vary the length of their hours. They divided daylight into 12 equal parts, so the hours in winter were shorter than the hours in the summer. Some of the oldest designs use water. This one's copied from an Egyptian clock, originally made from stone. The accuracy of the timekeeping relies on the speed of the drip, so the water has to be very clear or it gets clogged up. That's the problem I had with my water clock. For my latest clock design, I wanted to make something different, and most of all, to use a different source of power. This 19th century turret clock uses bicycle chain to support the weights. Turret clocks in general are quite relevant to the sorts of clocks that I make because the mechanism is very robust and designed to support heavy hands and which get blown about in the wind.
With the experience of building the water clock behind them, and with more new ideas, Tim and his partner set about designing another clock, a different design for a different site, and using a different source of power. This time a steam-driven clock.
Having made the decision to use steam, that created quite a lot of problems. I mean, all these elements do when you've never used them before. Neither of us had done anything with it before, and I wasn't really sure how to go about starting work on it. And I think that it lapsed for quite a long time then.
But in fact, what started me going was just the chance visit to a traction engine rally. I knew I wanted to have a steam whistle, and I hadn't actually thought of traction engines. But hearing all the noises convinced me that that was the way to do it. And of course, I suddenly realised the rally was very useful finding out more about them because the owners loved talking about their machines. I mean, I didn't know how a steam whistle worked before then. And I found one, a whistle off a 19th century American locomotive, complete with a bullet dent still left in it. Well, the whistle was a large one, and it had a 1 1/4 inch diameter inlet, which was obviously going to use up a fair bit of steam. And then we wanted to have some steam left over to power other parts. the site hasn't got three-phase electricity or gas, and I thought we'd just have to run off a 13-amp socket. But once I'd convinced myself that the big boiler was really worth having, we then found that we could run it off propane, but we may be able to get natural gas put onto the site at some future moment. Because it's a gas boiler, it'll have to be lit every morning and shut down at night. It'll also need flushing out at least once a week. The mechanical parts will need regular oiling, much more so than the water clock. The whistle will be eventually supported at the top of the clock, held by the central statue. People can read the time by the position of the weights down the side of the tower. The fall of the minute weight on the right is controlled by the pendulum. The weight is wound in each hour by the steam engine. The engine also moves the hour weight on the left down one division and moves the figures at the top.
Gee, Elmo, will you look at that?
As the minute weight reaches the top, it stops the steam engine and opens the whistle valve. I first tried making the figures out of wood covered in lead, but I quickly discovered that they'd be ridiculously heavy, so I started again experimenting with hammered copper. I've always been slightly obsessed by the pictures of the making of the Statue of Liberty, and that was all made out of copper, so I think somewhere in the back of my mind I've always wanted to have a go. I had various problems with the copper. Although it's quite easy bashing a dent in it, you can only get a sort of shallow bowl shape that way. To get a sort of complete hemisphere, you have to sort of squash the metal. It's called raising, traditional silversmith technique. And it's not obvious how you can bash a bit of metal and make it thicker. When I first tried, I seemed to spend a lot of time hammering the metal without achieving much at all. So I rang up a friend who works in the silversmithing department. He was very helpful. He gave me advice and a lot of encouragement. And I think after that I did have enough confidence and found it all a lot easier. Experts aren't always helpful. They can be terribly discouraging. You have to be careful who you ask. I've been using copper from old hot water cylinders, which means that the material doesn't cost very much, so it's not a tragedy if it goes wrong. I also like the idea of recycling things.
After making the figures, Tim started on the escapement mechanism. Making this took a very different set of skills from bashing copper. The design is based on the turret clock which Tim saw in the Science Museum. It's really quite a clever design. There are weights attached to the bicycle chain, so the chain's constantly trying to turn the pinwheel in a clockwise direction. But a pair of brass pallets check the turn of the wheel. Every second, a pin moves down and strikes the angled end of the pallet. This gives the pendulum an extra push, which is what keeps the clock going. There's obviously a lot of detailed machining and fabrication here that must have given Tim a whole series of design problems. So, we decided we'd try a little experiment. So far, Tim's talked about his various design problems with the benefit of hindsight. That's not the whole story, because he's actually forgotten many of the smaller problems he had going along. So when he got round to designing this, we asked him to keep a record of all the day-to-day problems he's had with it. Bright and early on day one, Tim went to work. He decided he'd start with one of the more complicated parts of the clock, and things didn't quite go his way.
I started with the pinwheel because I felt that that would give me a sort of feel for the size of and the strength of all the other bits. I spaced the holes around the pinwheel using a dividing head. When you turn the handle once, it turns the plate a 60th of a revolution. Previous attempts that I'd made without using a proper dividing head, I'd created an awful lot of work for myself because I couldn't get it as accurate. Once the plate was drilled, I cut the 60 pins and machined them down to fit through the holes and then riveted them into place. When I finished it and I stood back from it, I was able for the first time to sort of visualise how the whole thing was intended to work, and I realised that it wouldn't because I'd made the pins too fat and too close together.
Perhaps if Tim had planned ahead, in a little more detail, he could have avoided this problem. Nevertheless, he learnt from his mistake, and the second day saw some real progress.
My second attempt came out much better. I knew that with just a little more time that it was going to work. I'd sorted out the techniques, and it was much better too. The rivets were held in much firmer, and they all pointed in the right direction rather than being at funny angles. I suppose I was encouraged by getting the pinwheel right, and I went straight on to make the frame. Done much more fabricating than machining, so it's much simpler, much quicker really. So I suppose at the end of that day I was feeling quite pleased with myself.
Day 3, and Tim got on with the escapement mechanism. But here, the problem of the right choice of materials reared its ugly head.
I started making the pallets. I decided to make them out of nylon because they rub against the steel pins the whole time. I made the angles at the front of the pallet nearly vertical, the idea being that the pendulum is only given a push over a short part of its arc. It's supposed to make a clock more accurate. It's called a deadbeat mechanism. And by the end of the day, I'd finished the pallets and fixed them to the frame. I still hadn't actually got anything ticking, and I was beginning to feel a bit frustrated by this stage.
Day 4. Tim pressed on, hoping to get the clock ticking. Often, by this stage of a project, it's good for morale to see something working.
I made the bar that holds the pendulum weight, and at the top it has a bit of clock spring that fixes to the frame, which allows the pendulum to swing from side to side. And then I made a thing called the crutch, which attaches the pendulum to the pallet so that as the pallets move from side to side, it gives the pendulum a push. And with those made, I could actually try the thing out. I fitted a temporary weight onto the end of the pinwheel shaft and tried to make it tick, and it didn't. I tried fiddling around with it, and it still didn't seem much better. So I think I gave up for the day. In the evening, I did look at some reference books, though, and that gave me sort of confidence that it would work eventually.
By day 5, Tim was really into the prototype stage. The main problem now was friction, and those nylon pallets were also giving him problems.
The first thing I tried was putting the pendulum weight in place temporarily because the swing was terribly jerky. And I also smoothed the corners of the pinwheels down, and I found that in riveting them on, I sort of flared the edges a bit. I also made the angles on the ends of the pallets less vertical, and This gave the pendulum a stronger push. Not exactly a deadbeat mechanism anymore, but it worked better. All the things I changed improved it to one extent or another. But I didn't really like the noise it was making. And I also began to think that the nylon would wear out very quickly. And I decided that I'd try a set of brass pallets, partly because it'd make a nicer noise. Well, the next day I made the brass pallets. Much nicer stuff to work with than the nylon, and much more rigid. I think it felt a much better job. But then the thing didn't work at all, and I couldn't think what I'd done. But in fact, the problem was in the bearings. I found that by tapping the thing, I managed to get them in line, and then the thing worked much better. That day I was feeling quite pleased with myself. I made a temporary winding mechanism with an electric motor and a switch, so that when the weight reaches the bottom, it turns on the winding motor. Then the switch turns it off again when it reaches the top. And when I tried that out, it didn't work. The chain kept riding over the sprocket wheels. I solved that by grinding off the tips of the sprocket wheels so that they could accept chain that wasn't coming at them quite centrally. And then it worked fine. I chose this system of winding mechanism with the bicycle chain because its advantage is that the pendulum keeps ticking while you're winding it up. Most clocks, you have to restart the pendulum once you've wound it up. I think the main residual worry is the fact that the bicycle chain may not run smoothly. The sort of tensions that I'm running it on, it's much more likely to ride up than it is in its proper application. I'm not terribly happy about having a sprocket wheel with only 6 teeth in the middle. I think that increases the chances of it riding up. It's going to be outside. When it's fully set up, there'll be about 50 or 60 foot of bicycle chain, and only one link has got to seize, and it'll stop the whole clock running. I do think it's possible that we may have to use nylon rope instead, but that would slip around the central wheel, so it raises a whole lot of new problems, and we have to change quite a lot of the system at the same time.
I'm not exactly a typical designer, but a lot of the problems I have must be the same as those of any other designer. I tend to do the detailed designing as I go along. I work for a couple of hours and I stop and have a cup of tea and work out what to do next. If you're actually handling materials and trying things out, it sort of somehow enables me to think round a problem. I also really enjoy the process. I mean, it seems slightly magic. If something is completely described by drawing, making it very quickly becomes boring. It isn't creative anymore.